All right, so I'm not going to spend too much time on this lecture. It's not the most exciting lecture, but I think there's certain things that are just things you just got to know and memorize. So it's stuff that you don't have to be smart to understand. You just got to like put in time to memorize it, right? And then there's other things that are more conceptual that you have to learn the different principles so that you can apply them to a different situation. So I'm going to try to spend more time on those things because I think those are harder to understand, whereas the things that you just need to memorize, you don't need me to, help you memorize those. You can do that on your own. All right, so the stone part is pretty straightforward. You just have to know the types, know that they expand, right? And then know that, you just have to memorize, well, one is high expansion, the other's low expansion, yada, yada, yada. You have to know the principle that the weaker stones is partly because of the way that they're shaped. So we know that the harder stones, the one that has higher compression strengths, they're able to pack in more densely. Okay, so that should help you remember that principle. Again, there's 5 different types. Kind of know the uses for that. Type 4 and 5 are for a crown bridge. Type 3, we said, is used for dentures. And just kind of correlate the stuff that we use in the school and in your sim projects to what type. So whenever you're mounting something, you just kind of think, oh yeah, mounting plaster, that's a type 1 stone. Or when you pour something in microstone, oh yeah, that's a type 3 stone, okay? Or type 3 gypsum. And then same when you pour your final impressions. So we have sent your impressions to the lab. What type stone are they going to pour our impressions in? Type 4, right? So we had a slide about that. So know the water-powder ratio. There's just stuff you got to memorize. Nothing too exciting, right? So as though we pour ours in type 4 stone. This slide, if I were to take notes, I'd just say vacuum mix gives you a denser, stronger stone. This is a slide just saying that we use a type 1 gypsum for our mounting plaster. We'll get into the investment. Yeah, this slide is wrong. Just look at the pictures. You hand articulate those together. So again, just another summary slide. Type 1, type 4. Nothing too crazy about that. All right, byte registration. So we had a question on byte registration, and we wanted, so let me kind of phrase that. Let's see how it was phrased. Okay, so the idea is, right, this is our mouth, patient's mouth, and then when you make a registration, what material is that registration made out of? PVS, right, Regisil. So it's going to capture all the details of these embrasure spaces, okay? So that's our little piece of PVS. And then when you make an impression of the mouth and then you pour it in stone, well, it doesn't always capture all the detail, especially in these little nooks and crannies. So in your little grooves and also the embrasure spaces, if you look at the difference in, as I go back and forth here, you can see it doesn't capture it fully, right? So if you look here, we made it seem like, oh, this is kind of more blunted. Therefore, when you try to seat the impression material, well, obviously those areas won't seat as well in the cast. Okay, so this is for all you visual people. There's a little gap here because these areas are hitting first. So in order to eliminate that issue, we are going to trim that embrasure space so that you can now seat it down completely. Okay? So this is just a picture of us doing that. So you guys have all made your byte registrations. If you haven't done this part yet, that's all right. We can do it when we mount your cast together. But you see we take a lab knife and just slice it horizontally to remove this embrasure space, this area here, so that it doesn't interfere with our stone cast. I think some of you may have kind of misunderstood or mistaken this concept because not only do you have to eliminate the embrasure space to help you seat it fully, but you also want to eliminate any areas that are not a tooth-to-tooth contact. So the registration should be limited to areas between your preparation and then your opposing tooth, meaning that you should see space between the two. So the area that you put bite reg, you should see space. Okay. Here, this canine to canine, there is no space because they come in contact, and then you want to cut it there. Okay. So it's a different principle. So it's true you want to trim this part away because of tooth-to-tooth contacts, but here we're not talking about embrasure spaces. Specifically, we're talking about just eliminating areas that you don't have a gap between the prep and the tooth. Okay? So if that's not super clear to you, come up to me during class and then we'll try to explain that in better detail. Okay? All right, so we talk about tripodizing this cast, right? In this situation, this arch, when we hand articulate it, obviously is going to tip because there's absolutely no back posterior teeth. So the idea is that, well, we don't know what the distance is between the posterior teeth, so we need to fabricate this record base that's made out of acrylic and wax. So the wax is put on there so that we can quickly alter the height of it. So again, we have space between the two arches. Okay, so pink triad, which is UDMA, wax, and we're going to make our bite registration. So what material is this? This is a PVS material, and this is specifically Take One, which is what compared to Regicel? Well, it's more rigid and it sets faster, right? All right, so at this point now, since you have this registration plus the wax plus the record base, so just to be clear, the record base is, after it's made on the cast, you put it in the patient's mouth. And then when you put it in the patient's mouth, when you ask that patient to close down, you're going to find some space between the wax and then their teeth. Okay? And then, so that space that exists, you want to fill with this registration. So you do that intraorally first to get this record, and then you put this record back onto the master cast. Right? So master cast, I mean the cast that your final impression is poured from. And then now you can mount your opposing arch to that registration. Once you do that, then you know that this distance here from the prep to opposing tooth is accurate, and then you can make your crown to the proper occlusion. Okay? Yeah. Mm-hmm. Right. Yeah. So the triad is made, right? You just like your custom tray, you kind of adapt it, you light cure it, that hardens, right? And then you melt the wax so that you build up this little platform. So now the wax and the triad are like one unit. And then you adjust the height of the wax so until you get that kind of a couple millimeters of space when you try it in the patient's mouth, right? And then you seat that in the patient, well, it's seated in the patient's mouth, you squirt the registration, have them close, and then you capture this distance. Question? Well, the triad and the wax should cover the areas that are edentulous. So each clinical situation will be a little different. So this, in this case, is like a mandibular record base, and all these teeth are missing, so we're going to put and extend the wax and triad to the areas that are missing. Oh, well, yeah, when you first make it, you make it arbitrarily, right? But then you put it in the patient's mouth. And then, for example, most of the time you'll find that there's no space between the wax and the opposing tooth. You have them close, and then their teeth are already touching the wax. Well, what you do is you quickly melt down the wax so you get some space. Yeah. Or if it's, yeah. So that's typically what happens is you're removing the wax because you built it taller than you needed to. So the whole idea is that you need to have some space, otherwise you're going to have zero thickness of registration material. Okay? All right. So that's that principle. So record base is needed when you can't tripodize a cast due to an area that you have multiple missing teeth. Okay? Good? No? All right. Well, hopefully we'll get it by tomorrow. Again, come find me afterwards if you need a better explanation than I've given you. All right, so trimming the die, right? So I think this concept hopefully is important, or is important, also easy to understand, but you're going to remove all this extra stuff that's below the margin, apical to the margin. Remember we talked about if there's a little bubble that you find on your impression that results in a bleb of a stone, if that's below the margin, it doesn't really affect your crown because all that stuff is going to be trimmed away, right? So the reason why we want to trim this is that you need this kind of, you need this area here so your wax instruments can fit in that area and really contour and finish your wax ups nicely at the margin. You can imagine if all this stone is in the way, it's hard to fit a wax instrument to contour the wax. The other thing that I think one of the other questions on the exams or quizzes was that if the margin turns out to be flush with your gingiva for whatever reason, either you prepped it equigingival and then you didn't pack cord, or you didn't get impression material to flow beyond the margin, whatever the reason is, when you pour it in stone, if you can't clearly see that junction between the margin and the soft tissue, you're not going to be able to trim that die very accurately, right? So the difference between this die and then the mouth is that, well, in the mouth, the tooth is what color? White, I don't know, A2, yellow. And what color is your soft tissue? Pink. So when you look, can you tell the difference between tooth and soft tissue? Yeah, you just look at the color, unless you're colorblind. When you have it in stone, when you look at the stone, can you tell the difference between tooth and soft tissue? No, because it's all the same color. So in those situations, right, if you don't get impression material beyond that margin and into the sulcus, well, you're going to have a difficult time trimming the die at this step. So you want to mark the margin, put die spacer, and we'll start our wax up. So you wax it up to make it look like a tooth, and then you invest. This concept here, the thing that, if I were to take notes, the thing I would remember from this is that you want the crown to cool first, and then the rest of the sprue and runner bar to cool after the crown has already been cooled, right? So you have molten metal that flows here and will eventually fill this void. Remember, after you burn out the wax, there's just a bunch of empty space here, and the metal gets slung into this cavity here. So as the metal gets here, once it hits this wall, well, that's the area hopefully that cools first, and then this cools, this cools, this cools, this cools, and then the runner bar cools. Because the area that cools last is the area that you're going to find some porosity. So in this example, what happened was either because of poor setup in the sprue or poor positioning of the whole casting. So if it, you know, the center of the investment is where it's hottest, if you accidentally misplace this whole complex, and let's say the runner bar, this part cools first before your crown cools, then you're going to have the what we call a suckback porosity, right? And this is because the area that cools last is the area with the porosity. Okay? All castings contain porosity in the areas that solidifies last. So that's that principle. Question? Yeah. Okay. Yeah. So let's think of a scenario in which this complex, you see how, so this circle here, that's a little darker, this represents sort of the center of heat. So the middle of the investment material is where it's hottest, right? So a properly kind of designed complex will have the runner bar in the center of the heat, because it will keep this kind of melted as long as we can. Imagine this whole thing was, let's say, a little bit further down, where the crown itself was in the center of heat. Okay, so as the metal flows in here, well, because the crown is still in the center of heat, that stays molten a little bit longer, and then the runner bar cools first. So that's the scenario in which, you know, it would. Right. So yeah, that's one factor, and then the size of the runner bar or the reservoir, right? Same concept, same thing. You know, if you have a real small, let's say, reservoir for a large casting, maybe that, you know, since it's less volume, it cools very quickly. Okay. So that's suck back porosity. You probably need to know that. Again, just to reemphasize, gypsum is for high gold-containing alloys that melt at relatively lower temperatures, and this we don't use. We use in the industry now mostly phosphate bonded for crowns, and then ethyl silicate for our RPDs. Specifically, we use this Fuji Vest 2. It's a phosphate bonded at our lab. Okay, so the metals you guys know, don't need to go over that. Just specifically, we use either a noble or high noble metal at our school. We do not use a base metal alloy. All right. So you have to know. Yeah, let's go over these things. So there's 5 different things that I want you to know when you compare something that is, let's say, on one end of the extreme, high noble versus a base metal. So the base metal alloys melt at a higher temperature. The base metal alloys shrink more on cooling. The high noble metals, we would say, have better castability or are better adapted to the tooth. The base metal alloys are harder compared to a high noble alloy. And then the corrosion, the high noble metals are going to be more resistant to corrosion. Right? So how you can remember this easily by just remembering what a noble gas, right? Remember our noble gases in chemistry? Well, noble gases are stable, right? So you can think of metals that are stable, like high noble metals. They don't really corrode. Their chemical makeup doesn't really change, right? So that's that principle. You just, again, no concepts here. You just got to remember it. Questions? Okay, know your working and setting times for your PVS impression. So this is important because you're one day going to be in the clinic and making impressions. So you better have an internal clock in your head when you're loading, you know, or impressing around your preparation and your assistant is helping you load the tray. You should have a minute 10 countdown in your head, because at some point you want those materials to blend well. If you violate the working time, then your materials won't blend together and you're going to have separation of the two materials. And of course, setting time, you want to know that, because that you want to know how long your patient has to suffer while you got impression material all down their throat. Okay? So after 5 minutes of PVS, you can take that out. Okay, those are the specific properties of each material. So polyvinyl siloxane shrinks upon setting. Gypsum expands, right? What does investment material do? Okay, and then metals, great, good job. Nobody said any answers, so I'll let you guys figure that out. You can study that. Okay, any questions about, maybe this is going to be better if you guys ask questions about the FACEBO mandibular movements. Because, I mean, I could rehash this lecture, but I'd just be saying the lecture over again. So, yeah, let me throw out there. Any questions about, or what are your questions about this lecture? Okay, everything. That's easy. Okay, let me do that again because I know that part of the echo got cut off, right? Okay, first of all, let's just talk about what the conjugal inclination is. Okay? Does anybody remember, or should we just show the slide? Let's just show the slide. Okay, so an angle, it's an angle, right? So we'd say conjugal inclination is like 45 degrees or something. So what makes it make up an angle? Well, you got to have two lines for an angle to exist. What are those two lines? One line is a Frankfurt horizontal, which is represented by the line through the external auditory meatus, which is basically your ear, and then your orbital, right? So we can't readily get to the orbital, so what do we use as another point to help us? Millimeters, yeah. So the nasion is the point that's just above your nose here. Okay, so if you remember, go back and watch the video where we place that third point of reference right where that concavity is in your, right above your nose. Okay? So anyways, that's the Frankfurt horizontal, and then the other line is the slope of the articular eminence. So remember a question, yes? Yeah, but the line you can move kind of up and down, because an angle is an angle, right? So even if the line itself is moved up, well, the angle is going to be the same. So I drew it there just so the picture looks nice, because you get a nice little angle. Okay. So yes, correct. If I drew it technically where it is, but the important part is that the horizon. So I picked that same line. It's just it's parallel to it, just a little bit up. Okay. Right, so what's the principle we have to know here? So the idea is as your mandible translates, remember your mandible can do two things, just rotate, so it just hinges, and then it can also translate, which means that the condyle is moving down that articular eminence. So in what situations does that move down? When you protrude, and also in a lateral movement, one of the condyles travels down where the other rotates, right? Okay, so there's a couple scenarios in which your condyle will travel down the articular eminence. Question? Yeah. Okay, let me finish this and then we'll jump back here. Okay, so let's go to the extremes, right? On our articulator, which simulates a patient's mouth, we had set their articular eminence to 0. And then we simulated them protruding forward. What did we notice about the teeth in the posterior when it was set at a very shallow inclination? There's not a lot of space. Then we tried it when the inclination was very steep at like 60, and then we protruded forward. And what do we see? We see a ton more space, right? So the principle is the steeper your condylar inclination is, then the more space is created between your teeth as the condyle travels down or travels forward. Okay? So that's a principle you got to understand. And then when we apply that to clinical situations, so the question is, well, how does that affect what we do and how we make our crowns? Well, if you think about it, if when your condyle moves down and you have more space between your teeth, then that would allow you to make a crown that's a little bit taller and still avoid an interference, right? Because we know that as we move our jaws either forward or to the side, we want to eliminate interferences because of this whole concept of mutually protected occlusion, right? So if you got steep condylar inclination, we get more space in the posterior, which means that we can potentially make our crowns taller and still get away with not violating this mutually protected occlusion. So if you think about a taller tooth, well, our cuss anatomy, is that going to be steeper or shallower? You're allowed to have steeper cusp angles is another way to think about it, right? So something that's taller, obviously everything will be steeper, okay? Whereas if you had a more shallow inclination, obviously you have less space between the posterior teeth as your jaw moves forward or to the side. Therefore, you're limited in terms of the height that you can make the crown before it results in an interference. So that's the principle, right? Okay? So if we were to kind of carry this out and try to get some more good test questions out of this. Yeah, question? So if you take, let's say you have twins, okay? Everything about them is exactly the same except their conjugal inclination. One's at 0, the other is at 60, okay? When the twin that's at 60 protrudes forward, since there's a lot more space between the back teeth, right? You can essentially make the crown, you can get away with a taller, steeper cuss angle because you got tons of space there. You're probably not going to hit the opposing tooth. Okay.
Wouldn't that affect MIP?
Oh, good question. Okay, so does conjugal inclination affect MIP? Okay, so let's think about it this way, right? Think about where your condyle starts off. It starts off at sort of, let's say, the end point of that fossa, okay? When you're in MIP and you're just closing, what's that mandible doing? It's just rotating, right? There's no translation involved when you're just coming into a close, right? So those first 20, 25 degrees of opening and closing, that's just a pure rotation. So let's go back to those twins, right? One had a 0-degree slope, the other has a 60-degree slope. They're built exactly the same. When they close together, are their contact points going to be affected by the slope of their eminence? No, it doesn't matter because you're not even moving down that eminence at all, right? All you're doing is you're staying in that home position, you're just rotating around there. So the slope of that, right? Pretend two people are on top of the hill. I don't know, that's not a great example. I'm running out of examples. Anyways, the idea is that unless your condyle is moving down the slope, then the slope won't matter if you're not traveling down it, I guess is the point, okay? So in MIP, all you're doing is a pure rotational movement until you get to the end point. So you can think about it that way. Okay? Yes? Okay.
On the like 60, you
Uh-huh.
can have taller cusps.
Yes.
And I guess what throws me off is I'm thinking, well, those taller cusps occlude somewhere, and so how's that going to work? You know.
Right.
My occlusion.
Yeah, so you have to balance. I mean, obviously you're not going to make it tall just because you can in lateral. You have to balance that out in MIP, right? So I'm not saying, oh, make your cusp tips as tall as you have space, but the principle is you're allowed to make them taller. Okay. Right. Okay. Does that explain a little bit about conjugal inclination? So let me do this. So we talked about we want to set the articulator more shallow than what your patient would have in their mouth. So the average for a patient, we'll say, is about 45 degrees. If you want to avoid interferences, well, you want to set your conjugal inclination more shallow than what your patient would ever have. So when you guys get in the clinic, we generally have you set your conjugal inclination to about 25 degrees, okay? That way, when you test your movements on the articulator, remember at 25 degrees, there's a little less space so that we won't make our cusp or anatomy too tall or the cusp angles too steep, so that when you put it in the patient's mouth, you'll be safer and you won't be running into any potential interferences. Okay, let's get to your question.
I was wondering.
Okay. Right. So let's just first talk about working versus non-working, right? So how do you guys understand working versus non-working side? So let's say you're moving your jaw to the right, which is your working side, the right side, and your non-working side is the left. Okay. So to answer your question kind of quickly, it's potentially you can have interferences in both. Okay. So the reason for that is on one side, when you're moving your jaw to the right, right, what's excluding your teeth? Canines on the right side. Okay. So your working side, right? So in that scenario, the principle we apply is that, the difference between your triple tray and full arch articulator on the working side, right, is your arc of movement is different because the distance from your condyle to your teeth are different. So they follow a different path, right? So that was this example here, working side, okay? However, you can also move your teeth in a non-working side, so that's right lateral true sense. So then, yeah, so that the first part that we just went over was sort of this example, this whole series of slides. The other example, or the other point that we wanted to point out was this here. The non-working movement, well, the contralateral canine usually provides that disclusion. In this scenario, or this example, the left lateral intrusive movement, whereas the triple tray doesn't even have that tooth there to even guide off of. Okay, so we know that this isn't an accurate reflection of the patient's mouth. Okay, so yes, you potentially, in both directions, when you slide to the left and slide to the right, when you use a triple tray, you potentially could have interferences in both movements, because either movement doesn't replicate what the patient's mouth does. Right. Okay? Yes, question? Right, yeah. So if your condylar inclination is different than what the patient has, then yeah, the distance between the teeth are not going to be accurate. But if we set that condylar inclination more shallow, even if it's different, we won't run into an interference. Correct. Yeah. Okay. So we know that, yeah, if we use a triple tray, we know that the path or the arc of movement isn't the same. Therefore, we have a potential to run into the interference. So what's going on here is, if we have canine guidance, though, we're going to be a little bit safer in the sense we're going to minimize our chance for that interference because we have a gap between the teeth. Okay? So this whole kind of concept, I was trying to think of a good analogy. And then I thought of two people on a hill, and then I scrapped that. So this is the best way I could describe it. So we know that the Facebook mounted scenario, that's going to be the most accurate to what reality is. And by reality, I mean what the patient does, what the patient actually does, right? And then your triple tray is not a great estimation of what the patient is doing because the arc of movement is not as accurate, okay? So pretend you're in a car, okay? So instead of pretend you're in a car on a mountain. How about that? Okay, so anyways, let's go back. The idea is that we're trying to simulate the movements accurately so that we avoid an interference, right? Okay, so getting back to the car. Pretend you're in one car and then you have a GPS system, right? So we know that that's really accurate to telling you exactly where you are on the road. And then let's say you're in another car that doesn't have GPS. Instead, you're just has it turned off, and you're just using cell towers to help triangulate you. So gives you an idea of where you are, but not as accurate, right? And the idea is that you're trying to avoid an accident, okay? So obviously, if you're in the GPS system, if two cars both have GPS, you can whiz right by each other and avoid an accident because you know And let's say you're blind, so you can only drive based on what the GPS is telling you, all right? So if you're blind, you're just relying on the GPS. Or let's say you're in a driverless car, let's put it that way, okay? So they're both controlled by a GPS system, right? So because it's a good reflection of reality, you know you can pass by each other without any issues, right? So that's the face-bow-mounted full arches scenario. If you're using a triple tray, sure, you're in the vicinity of where you should be, but not nearly as accurate, right? So if you're driving around just using the cell towers, well, there's a potential you may run into another car because where the car thinks you're at isn't really where you're at, okay? So that's the potential for the, the difference. Okay, so how does canine guidance help us? Well, we know if you have canine guidance, that's one of the criteria we have in terms of, oh, it's okay to use a triple tray because having canine guidance minimizes the chance of a lateral interference because when you have canine guidance, guess what? You got a little bit of vertical space between the teeth, right? So canine guidance, and look at the space or the clearance you have. So even if the movement of the jaw doesn't reflect reality, you're still in the clear, okay? So the best way I can think of this is, let's say you're in that scenario, again, a triple tray, so no GPS in your car, and you have two cars moving and crossing each other. The equivalent of canine guidance is as if you have roads built at differing heights, like an overpass, okay? So even though when you look at the GPS, you're like, oh, you're going to hit each other, right? But because you're at differing heights, it doesn't matter that you intersect because the road is an underpass and the other is an overpass, okay? So that's the best I got for you, okay? So hopefully that helps a bit. Okay, so know your criteria for this question.
So when we talk about movement and depth,
Yes.
I understand like this, does that all come down to helping us determine?
Essentially, or crown contour, right.
Okay.
So if the space that you see reflects what the patient has, then you know, okay, I can make the cusp to this, or the crown to this contour and still be okay, not having interference. Because the whole idea is that we want to make this crown as accurately as we can so that when we get time to deliver the crown, we can just put it on and just be done with it. We don't have to grind the occlusion or adjust the occlusion, okay? Yes?
Let's say if you accidentally set the fur on an articulator.
Okay, yeah, let's go over that scenario, right? So let's say you didn't pay attention to this lecture and set your articulator to 60, okay? But your patient really has an inclination of 45. So what do we know about an inclination at 60 when you check your protrusive or lateral movements? We know that there's a lot of space between your preparation and then your opposing tooth. Therefore, when you design your crown, you think you can make your crown pretty tall, right? And still be in clearance when you move your jaw side to side. So on the articulator at 60, you'll look at it and go, oh yeah, my crown will be fine. I'm going to be in mutually protected occlusion. Okay? So you take that crown and the patient comes back and you put it in the patient's mouth. And then we know that the patient is at 45. So now when you tell the patient to move their actual jaw, well, guess what? There's not as much space between the prep and then the opposing tooth, but you had made your crown taller than it was allowed, okay? So that's the situation that you want to avoid, okay? All right, so you just got to know this slide, indications, contraindications. We'll ask you something about that, okay? So that is, well, let me wrap up with protrusive. So how do you get the patient's actual condylar inclination with a protrusive record? So you have them protrude forward, Most of the time, it's the edge to edge if they're class 1. If they're class 3, obviously, it's they're already at edge to edge or close to it. But the idea is that you need them to slide their jaw forward a bit. So when they slide their jaw forward, you're going to have some space between the teeth that you're going to fill with bite registration. And we showed the video of us putting the bite reg on the cast and then sort of manipulating the condylar inclination until it is fully seated. So that's the protrusive record. That's how you find the patient's actual inclination. Okay? Questions about that? All right, let's try to wrap up here as quickly as we can with here. So this is just a lot of stuff, not really to understand, but just to memorize, which is unfortunate. Okay, so we talk about you need to oxidize. You got to have other components in your metal alloy to serve as oxidation. So gold, let's say, so you may want to write this down. Gold doesn't provide any oxidation. So you have something that's like all gold, your porcelain's not going to bond to that very well, right? So that's the oxide layer. Base metals have thicker oxide layers. So they're more susceptible for a failure there. And then we'll get into cohesive versus adhesive. Just know there's a glossy matrix, a crystalline matrix. Glossy is for aesthetics. Crystalline is for strength. Understand the principle that your sintering temperatures decrease as you layer on, because you don't want to disturb the previous layers. Opaque, you got to know that it serves two purposes. One is to block out the metal, but also is the first layer, so that's the layer of porcelain that actually bonds to the metal. So sintering is basically just heating the porcelain up so that it hardens and sinters. Coefficient of thermal expansion, you have to know that you need to have a slight mismatch in the CTEs, that the porcelain should be a little bit less in terms of CTE than your metal, so that the porcelain is placing a little bit of residual compression. So if you want to remember that as the porcelain hugging the metal, or if the metal is pushing out slightly, however you want to remember it, I don't care, but the idea is that it should be in residual or slight compression. Question?
I know it's like the principle of expansion, the shrinkage.
Shrinkage of what? Right. So does a porcelain. Anytime you heat and cool, right?
They would shrink
It's not like a linear proportion, yeah. I mean, there's a whole material science behind it. I don't know if we want to get into that. So,
but when all is said and done,
all said and done, it'll be, yeah, you're going to have the porcelain. So, yeah, all I want you to remember, because this is like the classic board question is, okay, is it in compression or tension? I want you to remember that porcelain should be remaining in compression after it's sintered, and that's because of this mismatch in the CTE, okay? So the actual physics behind it, I'm not as interested in. It gets pretty complex. Yes? Did you have a question? Yeah, I thought you raised. Oh, no? Okay. Sorry, I thought you raised your hand. Yeah.
So if porcelain has a lower thermal
Yes.
expansion, does that mean it contracts more than metal?
Does it contract more than metal? I don't know. I don't really care. Just remember it's in compression. I mean, we can ask the material scientists. I mean, it depends what you're talking about, right?
Because then
So,
metal contracts slightly more than ceramic does. It has a higher expansion.
right, but it has a higher expansion, right? So then it'll try. Yeah. So it's all. I mean, again, it gets. Yeah, it's all relative. And we can go there if you want. Yeah, but let's do it when people aren't listening to us. All right, so know that principle. Adhesive, cohesive failures, got to know the definitions for that. Unsupported porcelain, this is a big one. When porcelain fractures here, is that a cohesive or adhesive failure? Cohesive, because it's within that material. So unsupported porcelain will fracture. It won't fracture at the interface because it's not the bond between the porcelain and the metal that's the problem. It's the fact that you didn't have anything really rigid here to support this area of porcelain. Okay, so that's that principle. So no adhesive cohesive. You're going to find some cohesive failures in the oxide layer, mostly found in base metals because, again, it's harder to control the thickness of that. Yes? Correct. So if you look at this picture here, remember they waxed this up to full contour and then did an even cut back, so they knew how much thickness of porcelain was there. And you can see from this metal framework is wider than this metal coping, right? So this means that this is better supporting the porcelain. Emily? Well, in this scenario, when you don't have the metal coping where you just dipped it and didn't do a cutback, and this porcelain here is too thick, the problem wasn't with the sintering of the porcelain. The problem was with the fact that you didn't have anything rigid underneath it to prevent it from fluxing and this fracturing. Yeah. There may be other situations where the porcelain, let's say you didn't use a vacuum, or there's some porosity in the porcelain for some reason. Then that porcelain is weak because of that, not because of the unsupported metal. Okay? You have differing margins. We said which margin had the best seal. Metal margins seal better than porcelain margins. You just got to know that. There's different designs. Don't have to memorize this, the actual configurations, but the critical concept is the contact points. You want them how far away from the metal porcelain junction? 1.5, yeah, so you don't want it contacting right at that junction. Survey crowns are crowns that support an RPD, and I want to show this because it follows the principle that, yeah, you can make your metal and ceramic any kind of dimension or design that you want. Okay, so this is an example. If you were a little confused, this is what a metal framework of RPD looks like, just for your visual. Lab prescriptions, you got to know what the important things, what the lab needs to actually make a crown. So reduce opposing, that's pretty straightforward. I feel like you reduce the opposing on the cast, then you reduce the opposing on the tooth in a clinical situation. Reduction coping, this is where you put a piece. So just know the sequence of this, right? So you have a tooth that's under reduce, and you have it in its die. You put a piece of acrylic that's well adapted to it. So the red part is a piece of acrylic that's adapted to it. Pretend there's no hole here. You take your burr, and then you adjust the acrylic or the coping plus the stone die. You remove that. That goes onto the patient's, or then a crown is made off of that contour of that die. This is the patient's mouth. You'll see the cope. Well, this shows that you can't see the crown just yet because you have to put the coping on to reduce the little bit that's sticking out. So if you were to pretend this is a tooth, initially a piece of tooth would be sticking through this little window. You take your burr and just slice that tooth structure down. Question? Yeah, lab, you can do it. I mean, yeah, whoever's making your crown. So yeah, here we would send it to the lab and ask them for a reduction coping. Okay, so just kind of run through the visuals there so you understand what the heck's going on. If you don't understand it, I'll try to grab an example from the Awatuki lab so we can show you. The last thing I want to go over is, and I don't know how to teach this well other than, there's 3 examples here of differing errors that you find. Okay, hopefully this helps, but there's going to be other scenarios where you may have a bubble in a different point at a different step of the fabrication process. So the best thing or the best advice I can give you to help solve these problems is draw them out. Well, before you do that, like really understand the whole sequence and the whole process. Okay, we talk about the intaglio surface versus a cameo. So know those terminologies, because I'll say something, oh, the bubble exists on the occlusal portion of the cameo surface of the wax up, or something like that. So know those definitions, know each step, and when it's a positive, when it's a negative, and then you essentially want to draw these out to help you identify. So read the question carefully, kind of understand the setup, draw the scenario, and then in your head just figure, okay, then I'm going to pour the investment, and I'm going to burn it out, so there'll be a hole here, right? Then it's going to be filled with metal, and then, okay, so you kind of have a visual of what it looks like, so when you try to seat it, you know if there's a discrepancy or not, okay? So the best thing here is, again, yeah, if you want, make up scenarios with your classmates and then ask them to solve it. That tends to work out pretty well. But these are kind of real-world examples of things, little errors that you're going to find, because not everything you do is going to be perfect. And then we get a lot of questions, right? Because we always get students that come up and go, oh, I got a little bubble here. Is this going to be okay? Right? And then the exercise we always make you do is, well, what do you think? How is this going to affect your final restoration? So this mental gymnastics of thinking through the process, I want you to start doing in the sim clinic, so that when you get to the clinic and you have certain errors that you identify, you'll be able to know that whether that impression, let's say, is acceptable, or do I have to put my patient through another 5 minutes of gunk in their mouth? Okay? So that's that principle.